Okay, well, good afternoon, everybody, and welcome to Lecture 10 of Physics 2820. Just before we dive into the actual lecture, we'll just do a little bit of a recap on how we worked on for test number 1. Now, from my perspective as an instructor, to be honest, everybody walked out of the class before the end of the test time. You all completed all parts of the test, so from my perspective, that worked out pretty well. Kyle should have already handed back to your copy of the test, and you should be able to see your grade on D2L. The results are mixed. Some people did very well, others not quite as well as you might have thought you had done. Please take a look all the way through that thing and try and figure out why I put X's in the places that I did X's. On D2L, I have posted a document that looks like this, test 1 answers. As all of the answers are there, so it's uploaded as a PDF document, so you can go back and you can take a look at what I was expecting. That's basically the lines all the way through. In particularly, these are things that we talk through class. Some of it's purely mathematical. This is what I meant by equations of motion, what you're actually solving, right? Not just F equals ma or something. You need to have the right equations. Generally, the numeric stuff was actually all done very, very well. And the only other thing I'll comment on is in terms of the question that said, why is this picture not right? I'll show you what I mean specifically. So if you remember, there was a question that looked like this one, and it says, a fellow student was looking for help. The idea here, what to jump at your eyes, if the code is the same, this algorithm works. This algorithm should work well. What's different about it? Well, you see the dots, dot, dot, dot. This is a time step of 1 second. That's far too large. The problem is the time step is too large. You got to make it smaller. Other than that, I think the rest of the question was done fairly well. Again, I was happy with this format because no one got caught trying to work out a bug. You were able to answer all the parts. So that was all pretty good. I said answers are posted, things are marked. So I think we can move on. Is there any other questions about test number 1 that anyone would like to talk about right now? Hearing nothing, let's dive in to Physics 2820, Lecture 10. Okay, what I want to do is I want to talk about numerical differentiation in integration. The idea here is we've been integrating systems of equations. The mathematics or the numerical analysis is the idea of doing numerical derivatives and numerical integrals. So consider a function. Imagine dealing with the function y is equal to x to the power 4. We know analytically that its derivative can be written as 4 times x cubed, right? Take the derivative, take the 4 to the side, reduce the exponent. If you wanted to say, what is the derivative at x equals 2? What you do is you stick 2 into this expression, and we're able to figure out that 4 times 2 cubed, well, 2 cubed is 8, 4 times 8 is 32. So that's analytically calculating a derivative. In terms of what that means, or one of the interpretations of that derivative, you can consider the following plot. This blue line is the function y of x on the y-x-axis. This orange line is a tangent line. At the point x equals 2, the slope of that line is the same as the slope of the function. That's what we mean by the derivative. Now, what if we didn't have a formula for the derivative? What if we didn't know what the derivative was analytically or in terms of primitive equations? How else could we go about finding the derivative? And the idea is we can go back to the definition of a derivative, so a Newton's quotient. Basically, the idea is you can talk about the difference between where the function is a small distance away, divided by that distance. Fundamentally, this expression is just contained in this figure, right? So what we're looking at here is for a given function, like y equals x to the 4th, to evaluate the derivative right here, what you do is you look at the secant line, that is the line between 2 points, figure out its slope, and then in the limit, as this distance between x and x plus h gets increasingly small, you approximate the derivative. That's the idea of a Newton's quotient. So for any finite size step, any step which is a number you can write down, you could approximate the derivative. If the step size is 0.1, then the derivative at x equals 2 at this location is the value of the function at x at 2 plus 0.1 minus the value of the function at 2 divided by the size of the step. So for this function, y is equal to x to the power 4. That's 19.4 divided by 16 minus 16 divided by 0.1. This is an approximate value for the derivative at this location. As you decrease the step size, h equals 0.01, you're going from x equals 2.01 back to x equals 2. This is what x to the power 4 would be, minus 16, but now you're dividing by a smaller time step. This is what ends up happening as the derivative. This is a closer approximation to the true derivative when x is equal to 2. If you recall, when x is equal to 2, the derivative is exactly 32. So this is getting closer. Now, I'll show you an example later on, but the idea here is you can't make h arbitrarily small. Once you make h too small, what happens is you basically get a 0 divided by a 0, and you know that floating point numbers on a computer are represented with finite precision. That actually starts to get worse and worse in the sense that you get like a 0 over 0 type thing, and numerically, the errors stop getting smaller, and they actually start to get larger again. So generally, the approximation improves as h gets smaller, but that doesn't work forever. Okay, so to talk about this example with an elementary derivative, a function that doesn't have a nice primitive derivative, rather than doing this one, let's do it for a different kind of function. There are lots of functions out there. You're familiar with sine, cos, log, exponent, x squared, x cubed. There's a whole bunch of other functions that have the name special functions. One of the special functions that exists is the Bessel function of first kind order 1. It has the symbol j1 of x. Now, what it actually is just a function. It exists. It's a real mathematical function that you may or may not have actually encountered before. And if I say, okay, here's the function, tell me its derivative, you might get stopped and going, I don't know what the derivative of j1 of x is. Now, it's a perfectly well-defined, smooth mathematical function, but it's not a derivative that I, or probably you, carry around in your back pocket as, no problem, I know what the derivative of j1 of x is. But what we can do is we can calculate the derivative numerically. So this special function, which in the SciPy library, scientific computing as opposed to numerical computing, is implemented as GV, what I can do is I can run that particular plot, and I can show you what a Bessel function of the first kind, order 1, looks like. It looks sort of like a sine that's decaying a bit. That's its shape. And if I was interested in trying to figure out the slope right here, what I would have to do is try to figure out the tangent line that goes to this point. So this is an example of the kind of problem that we want to be able to solve. Okay, so before I show you that answer, I want to take a step back and talk about different ways of approximating the derivative at that point. There are more ways than just using the Newton's quotient. So the first scheme we could talk about is we could talk about what's called a forward difference. So the idea of a forward difference is what we've been talking about to date. What you do is you approximate the derivative as the value of the function at a later point minus the value of the function at a current point divided by the time step. This looks very similar to the definition of a derivative, and it's called a forward difference because you're looking ahead for the function to try and figure out what the derivative is. That is one approximation for the derivative. But it's not the only one. Another approximation, and again, they're both approximations, is what you can do is take the current point of the function, f of x when x is equal to a certain number, and look backwards. That is, let x equal x minus h. This will be another approximation for what the derivative will be at the point x. These two numbers in the limit as what h goes to 0 are the same. But for any finite value of h, the slope of a line going through x and x plus h is not the same as the slope going between x and x minus h. These are two different numerical estimates of the derivative. There are other formulas out there. You can think about a centered difference. So a centered difference is this third one. What you do is you consider the point x. You're trying to figure out the slope or the derivative f prime at that x. You look at the secant line between x plus h and x minus h. Now, if you imagine that secant line, it's twice as wide, so you have to divide by 2h to get the slope. Again, in the limit as h goes to 0, all of these methods are the same, but they're going to give you different numerical answers, and each one has a different numerical accuracy or error associated with them. There are even more functions out there, and we can derive lots of them. Here is a 5-point scheme. So this is yet another formula that looks at the value of x previous step, the step before that, the next step, and the step advance. This is a 5-point formula, or it depends upon all 5 points of f of x as an approximation of the derivative. These different formula are all derivable with something called Taylor's series. For this one and this one and this one, it might seem obvious you're just doing a triangle. You're doing the slope, rise over run. But this last one, it may not be completely obvious why I want a minus 8 here and plus 8 here, minus 1 here and plus 1 here, and then divide the whole thing by 12. It works out that when you do the Taylor's series expansion, and we'll do a whole lecture on Taylor's series if you don't remember what it is, you can work out what these coefficients need to be so that this whole expression is equal to the derivative with a certain error. Okay, once I have these different schemes, what I can do is I can use them to approximate the derivative. Let's go and take a look at, that's not working. Markdown, raw, markdown. I don't know why that's not working. That's supposed to be a table. I don't know why it's not a table. Let's make it look like that as a table. It should render as a nice pretty table, but it's not today for me. Maybe it's rendering just fine for you. But the idea is you can imagine a table of data, something you might have collected from an experiment. Time is equal to, this is why this format's sort of nice. Yeah, maybe I gotta put more brackets in there. Nope, it still doesn't like it for whatever reason. Okay, time equals v, at time in v. This column are the times of some experiment. You're measuring what the speed is of something at time equals 0.1 seconds, 0.2 seconds, 0.3 seconds. And this column right here is the velocity that you measure something at discrete points in time. We can refer to those points as t underscore 0, t underscore 1, t underscore 2, all the way through. And likewise v underscore 0, v underscore 1, and so on. The data is forcing us onto a certain time step. We don't have the ability to choose any time step we want. The data only is known at these intervals, namely with a time step, 0.1, 0.2, 0.3, 0.4 of 0.1 all the way through. Yeah, I don't know why that's working that way. If you want to go and actually figure out the slope, which would be the acceleration, the derivative of v with respect to t, at a particular point. Say you wanted to figure out at this time, what is the acceleration of the particle? You can use one of the numerical schemes to figure it out. So if I said use the forward difference scheme, what we'd be doing is using the idea of evaluating the function at the next time step minus the function at the current time step divided by its time series. So just by hand, writing it out, no code involved, what you're doing is taking v2, which is this number, subtracting v1, which is this number, and dividing by the difference between this number and this number. So 3.8 minus 3.5 divided by 0.1 equals 3. Now, there's something about significant figures here. The act of estimating a derivative always reduces the precision. If I have a graph of velocity versus time, and it's a certain smoothness, the acceleration versus time will always be noisier. We go from having two significant figures to one significant figures. The act of taking derivatives always results in noisier output. That's just the nature of taking the derivative. It increases the error everywhere through. If we want to code this up and we want to do this as a Python program, I need to get this table, which for whatever reason is not being rendered right now as an HTML table. I want to get this into code, into the computer's memory, so I can work with it. There are lots of ways of storing data within the Python language. One method, and this is a method that you would encounter if you were opening a book on Welcome to Python, Introduction to Python Coding, Python 101, you would learn this method right away. And the idea is to use lists. A Python list is an ordered sequence of values, and inside of a list, you can put anything, including other lists. So one way of encoding this table of data is as a list. What we can do is we can say vdata is equal to the list, the first pair of numbers, the second pair of numbers, the third pair of numbers, and the fourth pair of numbers. Now, if we run that, then we can look up any one particular value in this table by going to the nth row and then choosing either the first value or the second value. The first value is going to be the time. The second value is going to be the velocity. The thing about Python is Python counts starting from 0. So we go 0, 1, 2, 3, 4, 5. So if I want to talk about the second row, that's the counter 1, and I want the time, that's the first thing in that row, I would say v2 over 1 equals 0.2. That gets me this number. If I want to talk about the velocity, I want to go with the second row, the second value, all the way through. So it's a way of pulling out these values. Observationally, by the experiment, the record is a time and a velocity pair. It's an ordered pair. It always goes together. We could use this construct to say, well, don't give me a particular number. Give me that entire record, the first or the second row all the way through. You can just talk about vdata all the way through, and that does work. Now, here's the thing. Conceptually, this is pretty easy. It just is really inefficient. Using lists and lists of lists is not a good way to teach the computer or tell the computer to actually store data in memory. When the lists are small, when they're just a few dozen things, it really doesn't matter. But if this wasn't a list that was this long, but it had a 100,000 rows or 1,000,000 rows, this would be a very inefficient way of storing the data in memory. It has to do with how lists are represented and the number of bytes the computer would need to use and how long it takes to index a particular point in this list and look them up and retrieve the data and other things to do with how Python is actually written. The solution is to use a numerically specific kind of structure, a kind of structure which assumes that the number of rows of items are all numbers, and every item in this list has the same length. Those are arrays. And in Python, these are called NumPy arrays, which we saw at the very beginning of the course. To use a NumPy array, it's almost the same as a list, where the square brackets indicate a list of rows. But what you do is you put it inside of an array. What that does is it creates an array data object. That is something in the computer's memory that's got all these numbers, but it's not stored as a list, it's stored as an array. Now, it works the same way as an array. If I want to look up the second row first value, that works. If I want to look up the second row second value, which is the velocity, that works just fine. And I can get the ordered pair. But now, this is an array, as opposed to just being a list. And that has performance implications. The data is in a numerical array. So if I just say vdata, I get back an array structure all the way through. Now, because of that, I can look up these values in a slightly more compact way. So rather than having to do vdata square brackets 1 square brackets 0, the second row, the first value. What I can do is I can get rid of these two middle guys and talk about them indexed as row column. Think about the array as a matrix. I'm in the second row, first column. So if I run that, second row, first column is 0.2. This idea of indexing or looking up columns can be more generalized when dealing with NumPy arrays, not with lists, but with NumPy arrays. And I'm able to say, you know what I want you to do is grab all the rows from row 0 up to row 6, but not including 6, and grab all of this column right here. So in NumPy, the notation would be vdata, give me the range from the 0, 1st, 2nd, 3rd, 4th, 5th, up to but not including 6, and give me all of this first column. And so that will give me back an array, 3, 3.5, 3.8, 3.6, 2.8, 1.4, this column of it. When you're talking about all of the columns in NumPy, what you can do is just say, I just want the slice that goes from the beginning to the end. And the short form of that is just a colon. So :1 just gets you the whole thing. If I want a single velocity pair, like as in time velocity pair, I can use the same notation and say I want the second row of data, but I want the ordered pair associated with that, 1, colon. Now, because it's an ordered array, it's a matrix of 6 rows and 2 columns. There's another choice we can make. We could also talk about this array as being 2 rows and 6 columns. And you can do this with lists as well, but we'll do it for arrays. You could also write this same data as an array of 2 rows. There's the first row. There's the second row. The first row now corresponds to all the times. The second row corresponds to all the velocity data. Of course, this is just a transpose. If I compare this array to its transpose, and that's what .t is giving us, the transpose of a matrix is just flipping these things so rows become columns and columns become rows. So they're really just 2 ways of looking at the same set of numbers, except when the data is written in this format, if I say vdata 1, 0 or vdata 0, 1, which one of these 2 numbers is a time and which one of these 2 numbers is a velocity, right? Is this one the velocity, or is this one the velocity? Or is this one the time, or is this one the time? Depending on how you set it up, that's a possible source of confusion. Now, for this particular way, v1, 0 is 3.0. We recognize that as being one of our velocities. So 1, 0 would be how you'd look up a velocity, and 1, 1 is how you would look up a time. If your data is stored by row, that is all of the t values first, then all of the v values first, what I can do is I can extract out the first row and the second row in terms of one-dimensional arrays. This is a good practice. Having a large dense array can be efficient, but sometimes you just want to address individual variables. You don't want to confuse your code by not knowing which one's which. So we just give it a name. We just say, look, this is the T array, this is the V array, and now it's very, very clear all the way through. Now, to be clear, if you started with the data like this, in this shape, and you did a T, V, you're going to get the error, too many values to unpack. You're expecting 2, as in the first thing and the second thing. But vdata.t, this is a thing with 1, 2, 3, 4, 5, 6 rows. So it's complaining, saying, you're trying to put 6 things into 2 things. That's impossible. Now, this might look like a much simpler way of doing it. You're like, okay, I'll have a T array, we'll have a V array. But as we've been seeing working with these dynamical systems, these physical problems, we could have more variables than just T and V. we might have a t variable, an x variable, a y variable, a vx variable, a vy variable, a vz variable, an ax variable, 3 for A, 3 for omega, a mass, a pressure, and a temperature. You could have many, many variables. And so sometimes your code is even cleaner if you can still name your arrays. So you can talk about this being the T array and this being the V array, but also have the benefits of being able to talk about all of your data together. One way of doing that is to use a Python data structure called a dictionary. So we talked about lists, arrays, and dictionaries. Dictionaries is the idea of taking your data and assigning keys that look up values. Any dictionary can be defined with curly brackets, key, value. And what that does is it structures our data so it has two parts to it. The T data, and the value of that is the entire T array, and the V data, and the part that gives to that is the whole velocity array. Now, we've seen that before, this idea of a velocity of data. We used it to pass back the results from our stepper functions. When we wanted to bundle up all of the results from the stepper, we put it into a dictionary and we yielded that back. But rather than yielding back just a single value, we could actually yield back the entire data set. In fact, this idea of looking up columns of data associated with the names, that's exactly what Pandas data frame is doing. A Pandas data frame is just the concept of using these dictionary-like things to name the columns, but it's given a new word, it's given a data frame. So what you can do is if you have that data in a data frame, not data dict, v data dictionary, you can get the whole thing as a Pandas data frame. Okay, so the thing here is these are different ways of representing groups of data. They all can be made to work, but there's benefits as you go higher up in the hierarchy. Now, rather than an array, I still have all my columns, but I get some benefits right away. The first one is just a better user interface. It's automatically coloring things. I can highlight on something. It's labeling my columns. It's talking about the 0, 1st, 2nd, 3rd, 4th, 5th row. So compare this to having to look at the data like this, or even worse, just as a list, as we did right at the top. There's much more structure in this Pandas data frame kind of way of doing it. The other advantage of Pandas is it supports a lot of operations, especially for time series. That is where the things are in time. Pandas can do things like not just compute averages, but it can compute rolling averages or interpolating or going to a different time scale. Lots of things when you're dealing with observations or something from an experiment and measurements, you often have a time series, a series of values at different times. Panda is very nice for manipulating those kind of time series. Okay, all of that is just a side trip down different ways of storing data in Pandas. Let's try and see how we can use that to now figure out what the acceleration is from our observational data. So however you want to build this thing, let's assume that we have loaded our data into a Pandas data frame. We'll see in a future lecture that if I have the data in a file, like a comma-separated values file, a CSV, or in an Excel spreadsheet, there is a one-line command that lets me load up that spreadsheet, like you would create in Excel, directly into a Pandas data frame. I think it's like read Excel, pandas.read Excel. So this idea of getting the data into this format is actually very easy because of the tooling that's built in there. If I want to figure out the acceleration at time equals 0.2, using the forward difference scheme, what I need to do is I need to compare the value at the second row to the first row. That's a forward difference. I'm looking at the 0.2. I need to compare this row to this row. So in code, that means the second value of v minus the first value of v divided by the difference between these two things. Now you might read through this and recognize the time step's always equal to 0.1. You could define a variable dt, or you could just let the math happen automatically. And what you get is that the velocity estimated between here and here is 3.0, or 2.99999 within precision of the system. Rather than having to code this up for every single line separately, it's helpful to introduce a function. A function is a rule, a Python function is a rule that takes data in and gives you some response out. So here is my Python function that computes the finite difference for data. The finite difference, F50, of some data type, okay, where it's represented as a Python data frame, for the ith row, the 0, 1st, 2nd, 3rd, 4th, 5th, can be written as the data on the ith plus 1 row minus the data on the ith row divide by the difference between the time on the ith plus 1 row and the ith row. The idea here is this first column that doesn't have a name, this is I. I equals 0, I equals 1, I equals 2, I equals 3, I equals 4, I equals 5. This rule allows me to figure out the derivative at any row. So if I want to figure out the derivative for the first row, my function is just f data comma 1. And that gives you this thing right away. So let's use that function to actually go ahead and compute the derivative or the acceleration at every point. Let's start with a plot to visualize it. This is what the data looks like. Okay, I've got time along the horizontal. I've got velocity along the vertical. This is the 0, 1, 2, 3, 4, 5. There's 6 points in all. And what I want to do is I want to calculate the acceleration or the slope at this point, this point, this point, this point, and this point. Using a finite difference scheme, what I need to do is I need to call this function, f data, for this value goes from I equals 0, 1, 2, 3, well, 0, 1, 2, 3, 4, all the way through. Now, before you go about doing this, it's helpful to create a column inside your data frame to store the answer. This isn't strictly necessary. There are other ways of doing it, but I'm going to strongly recommend this technique because then you won't get confused about the accelerations you're unable to collect. This command creates a new column called A, and I'm filling the entire column with numpy NaNs. NaN just means not a number. It's a shorthand for null, or I don't know, or something that I haven't figured out yet. It's not a 0. I just don't know what it is. So to be very clear, this is what it looks like before I run this command. If I run this command and I look at vdata again, what I've done is I've added a new column of A's, and for every row, it's a not a number. It's just a blank. I'm going to fill it in. Now that it exists, I can talk about it and put in the real value. I can use a loop to loop through the 1st, 2nd, 3rd, 4th, 5th row. And for every one of those values, so I can calculate FD on the data on that row and store that information inside this variable at this row. Okay, now there's some subtleties here. N represents how the length is. So how long is this array? 1, 2, 3, 4, 5, 6. There are 6 rows, N is equal to 6. But I can only do the loop from here, 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 and here. I have to stop one early because a forward difference always includes this value and its difference. Or this value and its difference. To compute the forward difference estimate of the derivative for this column, this row, requires knowing what the value is in the next spot. And we don't know that. So if I run that loop all the way through, then I now have the information of the acceleration, but I never will know the acceleration at the end because that requires knowing what the velocity will be a time step later. Some common errors that you might get. Let's pretend, for the sake of argument, you did the wrong thing, and you just loop through all of the errors all the way through, you're going to get an error. Why an error? Why am I getting a key error? Because inside the code, remember this function that's actually doing the work, it looks up the next value, subtract the current value. Well, in this loop, when you're at the last row, you can't look up the next one. So this kind of error of a key error 6, I don't know what row 6 is. There is no row 6. I only goes from 0 to 5. So that's a common error that sometimes occurs. And the other thing that one might notice is I'm using two ways of referring to my rows. You may refer to them as V square brackets A. This is a lookup, but this will also work just fine. You can use either notation you want. There's a question in the chat asking, to figure out the derivative in this last row, could you use a backward difference? Yes. And that's why there's these different schemes. So if you want to figure out the derivative here, I could compare this value to this value. It would be a different numerical algorithm, but I could do that. That's why there's more than one scheme out there. Okay, let's plot this data and see what we get. This is now a plot of the t data and the a data. Time along the horizontal, acceleration along the vertical. 1, 2, 3, 4, 5. You see this last value, this nan, doesn't even appear. Okay, so what it's doing is it is correctly getting rid of all of the of that nan. It just ignores it. So if the first plot had 1, 2, 3, 4, 5, 6 dots, this plot has 1, 2, 3, 4, 5 dots all the way through. So this is a nice way of handling the fact that this has 6 numbers, this only has 5 numbers. You have to have the same number of things, so let one of the things be not a number. Okay, let's go full circle back to this function that we talked about that didn't have an elementary derivative. Let's go back to trying to figure out what the derivative is of a Bessel function of the first kind of Bessel function of order 1. So again, here is the function I'm interested in. It's a function that's sort of wobbly, but it decays as it goes away from 0. It's called a order 1 Bessel function of the first kind. And I'm interested in figuring out what the slope is at every point. To make this graph, I evaluate it at discrete points. This is the ordered pair of data all the way along. You don't have to use pandas data frames if it becomes more confusing. If you've got your data already in NumPy arrays and you're not going to get confused about how you're using it, leave them as NumPy arrays. There's no need to go to NumPy arrays to go to pandas data frames if you got this working. Pandas data frames gives you some added functionality, but sometimes it may not be what you need. So let's just try and figure out the derivative of this function using just NumPy arrays. Here is a scheme that computes the derivative of x and y data on the ith row using the using the center difference approximation. So this is a function that computes the finite difference in a center difference approximation. What I'm doing is comparing the function, the point ahead, the point below, and then the difference between those two things. So if I want to compute the derivative at the 8th point along here, what I would do is pass in all the data, all the x data, all the y data. That's the data set together. Remember, I'm no longer using data as a column, so I have to list each one of these independently. And then I could run that function. I could figure out for the 8th value, 0, 1, 2, 3, 4, 5, 6, 7, 8. Right there, its slope is approximately minus 0.36. That seems about reasonable. Okay, some warnings. In Python, you use square round brackets to call functions. If there is a round bracket, FC round bracket, FC round bracket, that means it's a function. Functions take arguments, and arguments get evaluated by functions, and you return something. Round brackets mean functions. Arrays, lists, data frames, dictionaries use square brackets to look up their values. So y is not a function. Y in this particular piece of code is an array. If I want to talk about the first, second, third, fourth value, I use square brackets to look it up. Square brackets can be used for dictionaries. You could say data open square bracket and then put a string. You could use it for lists. My list open square bracket and then a number. Square brackets are used for lookups. It is often the case that when you're debugging your own code, you will encounter a problem where you should have used square brackets and used round brackets, or you should have used round brackets and used square brackets, or getting it confused in some way. If I have an array and I pass in round brackets, it thinks that I'm trying to call the data array y as a function. And it says, this is not callable. Likewise, if I have a function, I can't look up its value. Function object is not scriptable. These kind of problems will tell you whether or not you've used square brackets or round brackets in the incorrect way. Another kind of error which comes up from time to time is often people say they wanted to calculate 16. You, of course, know that 16 is 4 times 4. But because you use variables, sometimes you might write that down. Here's an error message. Int is not callable. Because you're writing, what you're asking the software to do is take this thing, treat it as a function, and then call it with the arguments of 4. And what it's telling you in big red response is, I have no idea what you mean by using 4 as an integer. You can't do lookups on 4 either, but it's that idea. Okay, so lookups, functions, round brackets, and square brackets. You will encounter those errors. Everybody encounters those errors. Think carefully about whether or not it's a function or a square bracket. It's a very common error. Okay, how do I actually use that? What we can do is I can loop through all these points to compute the derivative of this Bessel function. We're going to start by creating an empty array to hold the output we're about to calculate. Right? We're not just going to go calculate. We're going to create some structure that's going to hold the answer. Now, if we're not using data frames and we're using arrays, we have to create an empty array that's the right length. So what I'm going to do is figure out how long the data is. The length of this and the length of this are the same. You can choose either one. So I'm going to figure out how long it is, how many entries there are. And then I'm going to create a new array which is filled with nans, but it has the right length. Let me show you what a few of these commands do. First of all, len of x is saying how long it is. There are 40 points in this array. If I say np1s of 40, I am getting an array of 41s. And I could put in a number or a variable. The thing about numpy numbers is not a numbers times anything is not a number. That's what dy dx is. It's just an empty array of length 40 filled with I don't knows, to be determined, not a numbers. Now that I've got that data structure, I can do lookups on it. And I can look up and put into the ith position the central difference of the data set at the ith column. Once I've got all that, I can make a plot. And this guy is the derivative of the Bessel function. Now, if you want to, you could stick that in there to make it very clear. We can make this plot even fancier, and we could say, okay, this guy right here is j1 prime of x. Let's make it all pretty and fancy. Valid syntax. right? We know that if I want to label that, I could do a plit.legend. Okay, and then maybe I want to this is why there's two types of quotes. There's the derivative, but maybe what I want to also do is on the same graph, plot the original data. So there you go. There is a function of, in blue, that's a Bessel function, and then in orange, that's its derivative. We've numerically calculated the derivative at every point along, except for the last one. So there's a one-to-one mapping here. Every x, if I could just read it properly, because, yeah, you have x's and y's, those are all the same. It's just when we get to the very end here, see this guy right here? This one goes one further because there isn't a point for it to connect to all the way through. No, wait, doesn't seem like it's lining up here either. What am I missing? Oh, let me do this. Let me put in some horizontal lines, and then this will make it clear. I'm going to put a horizontal line at the first value of x, and I'm going to put a vertical line at the second last value of x, and this will make the plot easier to see. Alpha is just a way of making like faint colored lines. Here, let me draw in two more lines, and this graph will be that much easier to visualize. There we go. Okay. So the derivative I'm calculating at the second value and the second last value. The reason is I'm using a center difference formula. A center difference the formula depends upon the current value, the value to its left and to its right. And because of this, I have no way of knowing what the derivative is at the first point, and I have no way of knowing what the derivative is at the last point. This idea of using nans keeps this all organized. So if I actually take a look at dy dx, it's a set of numbers, there's 40 of them, but the first one and the last one are nans. As was pointed out, if I really wanted to fill it in, I could calculate the derivative at the first point using a forward difference. Okay, so imagine I, by hand, calculate the derivative at the beginning. See, it fills in that point. And then what I could do is I could calculate the derivative at the end using a backward derivative. So what would that mean? You're taking to figure out the derivative right here, I'm looking the difference between these 2 points. I'm taking the last position minus the one before that, the last position minus the one before that. And that's the derivative at the end. So now that I filled in the remaining 2 entries, I've got the derivative all the way through. So you can combine these methods. So here I'm using a center difference for all the orange lines except for the last 2, and then I did it only at the end by hand. Okay, we're going to do a lab that involves you doing numerical derivatives. This should all seem, on one hand, both like really trivial, and he went through that very slowly, but it's also a little bit tricky when it comes to what do I actually type in. When we get to an assignment on this and a lab on this, go through it. Make sure you really, really, really know why it's a 1 and not a -1 and not a +1 and not an I and not whatever other letter. It's important to be able to actually understand what's going on here. Now we've done derivatives, there's a second half to the problem, and the second half of the problem is integration. So if we know how to differentiate things, we should also know how to integrate things. So let me talk to you about numerical integration. Numerical integration is the idea of figuring out the area under the curve. What we want to do is we want to estimate whatever this thing happens to be, the integral of some function. And one way of doing that is an approach called the rectangular rule. What we do is we divvy up the area under the curve into a bunch of rectangles, starting at f equals a on the left-hand side, going up to f equals b on the right-hand side. And these rectangles all have the same width, b minus a divided by n, if n is the number of rectangles. And the heights are given by the functions. And then what I can do is I can add up the areas of all these rectangles, the area of the first rectangle, second rectangle, third rectangle, and so on, as a sum. And this would be an approximation for what the area under the curve happens to be. Now, in terms of a picture, these are some notes from previous offering of the course, but it's the same idea. To figure out the area under a curve, we can approximate that by a bunch of rectangles all the way through. In general, there's a beginning and an end, an a and a b for any integral. We can consider these rectangles to all be the same size in one version of the algorithm. We divvy it up into a number of different rectangles n. If b minus a is the total length of the window, and there are n rectangles in total, delta x is the width of every rectangle. This point, this point, this point, this point, this point are given by this expression all the way through. So I can figure out what every value is along the function. And then what I can do is just figure out the area of each one of these rectangles, fi times delta x, and add them all up together. That's called the rectangular rule. So whether or not you write it out by pen and paper, you do it by math, you do it by sketch, the idea is this is a formula or a method that lets us figure out the area of any function. You need a few things to make this work. You need to know what the function is. You need to know what the lower and upper bound are. You need to know how many rectangles you want to use. I could code this up as a generic Python function. Here's what such a function might look like. NIREC, numerical integration using rectangular rule. It depends upon four things: what the function is, what the left bound is, the right bound is, and how many rectangles to use. I can calculate from a, b, and n what the step size is. The actual algorithm is just to add things up. This idea of taking a sum can be written in Python as sum equals 0, and then for every rectangle, evaluate the function at that point. You're stepping through xi equals 0, 1, 2, 3, 4, x1, x2, x3, x4, multiply by dx, and add them all up together. Now here's the thing. This first argument, that's a function. It's not data, it's a function. You know it's a function because it can be called. We talked about round brackets mean functions, square brackets for arrays. This function, see how I say f round bracket? That means this is a thing that makes sense to pass arguments to. In Python, not only can you pass integers, dictionaries, lists, and arrays to functions, you can actually pass other functions. Which is weird, but I'll give you an example. Here's a very specific function. The function is sine. Not sine of something. Sine of something is a number. It's just a function. It's just the sign. A and b are numbers, n is numbers. That is the integral of sine of x from 0 to pi over 2. Now, I can evaluate this analytically because it's one of the integrals we know how to do. And the integral of sine of x, antiderivative of sine, is a minus cos. Evaluated the upper limit and the lower limit. The true answer had better be 1. So this is an approximation, right? But that makes sense, because if you go back to this picture of thinking about a bunch of rectangles, you see this little area right here, right here, right here, right here. That's the error. It's missing a little bit of the area underneath each rectangle. That's why you're not getting 1.000. You're getting 0.919403. You have an 8% error. How do I reduce the error? More rectangles. more finely divide this thing into parts. If I have the same function, the same points, but I have 100 rectangles, now I get an estimate of the integral of 0.9921. That's a lot closer to 1. I've increased the accuracy by increasing the number of rectangles. Now, it's not perfect, right? Even if you have 1,000 of these things, it's still not 1, or 10,000 of these things, or so. It's getting closer and closer, but it's not going to be 1 exactly. Now, mathematically, an integral is defined as the limit of this sum. If I could let n be to infinity, this would work, but that would take a forever amount of time to run the program, okay? If I use billions of rectangles, it's possible, depending on how expensive it is to evaluate that function, this could take a really, really long time. There's always a trade-off between how long you're willing to wait and the accuracy you want out of any numerical model. Now, this f and the a and the b and the n are just the names I'm giving to the function. The fact that f, a, b, and n are used inside the definition of the function have absolutely nothing to do with how they're used when you call the function. So what I could do is I could define a new set of functions. I could have a new function called the g function. Well, the g function is 1 over x squared e to the x squared. I'm just calling it g of x. I could give new values for a, b, and x. And now this routine, which is the same function, is taking as arguments g, a, b, and n. And the integral of this function from 1 to 2 is approximately 4.88. It doesn't matter what I put on these 4 values. They're just being passed in order to the original function. So I could use other names for these things. I could call the function my function. I could call the lower limit 2.3, the upper limit 10.2, and the number of rectangles 100. And if I wanted to, my function, lower limit, upper limit, number of rectangles, that would be fine Python code. You're just passing in these values in order all the way through. It still works. Turns out the integral from 2.3 to 10.6 of this number is something close to 1008. Now, sometimes when I'm running these kind of functions, right, what I might want to do is I might want to pass in true values, right? I may want to just pass in 2.3, 10.2, and 100, right? I might want to pass in just hard-coded values. What's the equivalent to what is this thing? Not its name, which requires a definition, but like what it's equal to. How would you do something like that? And there's a way of doing it, and these are called lambda functions. There's a concept in programming called anonymous functions, or unnamed functions, or lambda functions, all the same kind of idea. This is a function which has no name. Now, it has no name, so we typically call the function a lambda function because we use the letter lambda in Greek to represent it. But the idea is just the rule that takes an argument to an output. That's the function. I don't really need to actually give it a name to be able to do it. I'm only introducing the name so I can call this function. So what I can do is I can use a lambda function all the way through. This is another way of defining functions in Python. It's very similar to the idea of def, my function, argument, return, except for what I'm doing is saying, okay, G is the name of the thing, X is the argument, lambda is a keyword, colon is saying this is what you're going to return, and this is the return stuff. You can always write any lambda function in this format. It's just a slightly more compact way of doing it. So I'll show you the comparison between these two things. This would be the verbose way of doing it. This would be the compact way of doing it. For functions that are more than one line, you always would do it this way. lambda functions are really nice when they're small little rules. A small little rule that you just declared the function for the purpose of passing it to something else. In the sense that, rather than doing ni rect g, a, b, and n, I could actually calculate the integral of the function y goes to 3y squared plus y, comma, 2.3, 10.2, 100. Or I could calculate the function, so that would work. Or I could go to the function x goes to this bit. It's a rule that goes from something to something and figure out that number. I better use the same numbers. 1. Oh, no, right, that's what I was doing. This is that example. That number and that number are the same. The point is, there are compact ways of using these kind of functions. You could just pass in the raw value, what the function really is, without giving it a name. That's what a lambda function is. Okay, so there's error associated with any rectangular rule. To get the correct answer, you need to add more and more rectangles, and you'll approximate the answer. But there's an improvement. And what we can do is use a different kind of rule or method to figure out the area under the curve. A more accurate method is something called the trapezoid rule. Okay, there's the formula. But I don't want you just to go, there's the formula. I want you to be able to understand where the formula comes from. So here we go. Back to some notes from a previous offering in the course. Okay, trapezoid rule. Rather than thinking about the area under a curve as a rectangle, think about this shape as the area under the curve. Approximate the area under the curve between 2 points. As a line segment on the top is going to be sloping, this is a trapezoid. This line and this line are parallel. The area is going to be the area of that trapezoid. And the area of a trapezoid is its height, h, divided by the average of its two sides. All right, you might remember this. If I take the average of this value and the average of this value, so fi plus 1 divided by 2, that will give you, and then multiplied by the height, that will give the area of that rectangle. If I have an interval from A to B, I can divvy up that interval into a number of trapezoids. So if I have n trapezoids, 1, 2, 3, 4, 5, 6, 7, 8, 9, n, I'm divvying up the partition. So I go x0, x1, x2, x3, x4, all the way up to xn, but there are actually xn plus 1 dots along this graph all the way through. There's n plus 1 points, gives you n trapezoids. Where those points occur is the same as in rectangular rule. It's given by a spacing of h, or delta x, or whatever you'd like to call it, b minus a divided by n. That's how wide each one of these things are. And these are the points in here. That one, that one, that one, that one, that one. The area under the curve is approximately equal to the area of all the rectangles added up together. The area of any one rectangle can be written as h divided by fi plus 1. This is the area of the ith rectangle. So the first one, the second one, the third one, the fourth one, the fifth one, adding them all up together, these are all these areas. Summation, the brackets are not needed. Everything is being multiplied by a common factor of h over 2. So let's bring that outside. And what I have inside here is 1 f1, but 2 f2s, 2 f3s, 2 fn's, 1, 2. So what I can do is take that factor of a half, bring it inside the parentheses. Bring that 1/2 inside and divide by the 2, divide by the 2, divide by the 2, except for the very first point and the very last point don't have any other side to match up with. So we're left with a formula that says the area underneath the curve is F1 divided by 2, the last point divided by 2, and then the sum of all the interior points minus h. This formula is very, very close to rectangular rule, but as we will see, it has much better numerical properties. Okay, I'm hoping that you should be able to, with a piece of pen and paper, sit down for yourself at any time in the future and come up with this rule. Starting from this little cartoon, you should be able to, which I'm really asking you to sit down and go and do it at some point in your life, preferably before a test, and give me this sketch, give me this logic that explains where this formula comes from by explaining that I'm building it up by a bunch of rectangles all the way through. Rectangles, trapezoids. Okay? Notice that we're evaluating at the first point and the last point, and we do the sum through the middle. Right? Notice that the rectangular rule only needed to be evaluated at the left-hand side of each interval and never at the last point. But the trapezoid rule requires being evaluated at every point, including the very last point, all the way through. Right? And that's a subtlety. That's really the only difference between the two schemes. Other than that, they're basically the same. Here's how you would implement such a scheme. I have to have some function I want to integrate. I have to have a left and right boundary, and how many trapezoids I want to use. This is how big each spacing is. I can start by evaluating these parts right here, these parts on the left-hand side. That's the initial part of the sum. And then going from 1 up to, but not including that last one, I can evaluate all those other guys. I don't like that code. That's not right. That's not right. But maybe it is right. The integral should be 1. Oh, I am right. Oh yeah, because I'm going up to that last point. The last point includes it. Okay, that's fine. That's fine. We're all good. Don't worry about me. It's my brain. Okay, so we're evaluating the first point and the last point and all the points in between up to n minus 1. When you integrate up to n, that goes up to but not including n. So it goes from 1 up to n minus 1. So this is the trapezoid rule. And if you look at the integral of the sine function, which analytically is equal to 1, with 100 rectangles, you get an accuracy of 0.99. With the trapezoid rule, you get 0.9999, right? Even with fewer rectangles or trapezoids. Can you see how much better the trapezoid rule is than the rectangular rule? The rectangular rule is conceptually slightly easier, but for really no more computational effort, you just need to evaluate for one more evaluation, always use the trapezoid rule in any real integration. There are other schemes to evaluate numerical integrals, and we'll cover those next week. Okay, so this is how you would integrate a function, but how would I go about integrating data? What if I don't have a function that I could pass in as such a thing? Well, it's similar to what we did for derivatives. If I want to integrate some data, so let's go back and consider this array. I have the velocity data. Say I want to compute the displacement. That is how far an object with this velocity versus time graph has moved. I've got 6 points, 1, 2, 3, 4, 5, 6. So I can only do 5 trapezoids. I can't do any better than 5 trapezoids. That's all I got. In terms of data, this is what we're thinking. Here are the dots, 1, 2, 3, 4, 5, 6. There are the known data. And what I'm thinking about is these trapezoids, right? All the way through. Trapezoid, 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 5 of them. This is just a little cute plot that's drawing basically a trapezoid. Point-wise, point, 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 point. 1, 2, 3, 4 points all the way through. To figure out the displacement, that is how far an object moved between the time 0.1 and 0.6, the formula, using the trapezoid rule, because you're always going to use the trapezoid rule, is a half of the first point, a half of the last point, and then the sum of the points all the way between them. All the way between them. Oh, wait, I'm missing something. There, I equals 1 to 4. So if I wanted to implement that, what I'd want to do I'm going to do it like that, is maybe have a function called ni trap data. So not ni trapezoid, but ni trapezoid for data, where data is a pandas data frame. I can look at the data and figure out what the time step is. I could just take the second point and the first point and take the difference. That will be the time step. I can look at the number of points to figure out how long the data is. That's going to be 6. I can calculate these first two parts expressly. I can take the first value and the last value. And then I could loop through, adding up all of these points together and multiply by the sum all the way through. So if I want to figure out the integral of this function, I would just figure out its displacement. And its displacement is 1.59. And you could sort of look back here, and you could think about the area of this thing from here to here. This width is 0.5. If you imagine a rectangle if you think about this rectangle, that rectangle has an area of 1. That rectangle has an area of a half. So it makes sense that this remaining part has an area of about 0.9. That seems reasonable that we have implemented the algorithm correctly a little. And we could always check with some other function all the way through. Okay, so this has sort of been a very careful derivation of numerical and derivatives and numerical integrals, talking about how we do it for both functions and data, and being very careful about how we're storing that data all the way through. On Tuesday, I'm going to do some comparison of the accuracy between rectangular rule and trapezoid rule. We'll end the lecture at this point. We'll talk about another numerical method called Simpson's rule. We might talk about Taylor series, but I'll have a lab for you that you'll get to do some numerical integration, numerical derivatives yourself. But I think this is a good point to pause in today's lecture. It's just at that hour and 15-minute point. So is there any questions on this material that we should talk about? And if not, I'll end the lecture here, and I will see you virtually next week. There's no lab today, and there's no assignment due. So enjoy a couple days break. We'll see you next week.